Hello everyone, welcome to this online marine seismic data processing course. In this presentation, I'm going to talk about correlation and its applications in seismic data processing. So I'm going to give you a brief introduction about the basic definition of correlation and its mathematical implementation, followed by some real seismic data applications. Okay, so basically correlation is another type of time domain operation that helps in the measurement of the similarity or the time alignment of two seismic traces. It is very similar to convolution, involves progressive sliding of one waveform past the other, and for each time shift or lag value involves summing of the cross multiplication products to drive the cross correlation as a function of lag value. So basically, if you have two finite length digital waveforms xi and yi of elements from 1 to n, the cross correlation function is given by phi of xy tau. Tau is the lag value and is given by the cross summing of the cross multiplication products xi plus tau, tau for that particular lag value, yi. So in simple terms, if we consider a real example, so let us consider these two wavelets. Wavelet 1 is 2 comma 1 comma minus 1 comma 0 comma 0, and wavelet 2 is 0 comma 0 comma 2 comma 1 comma minus 1. So basically wavelet 2 is shifted by 2 samples in compared to wavelet 1. So the time lag at which they are most similar can be determined using cross correlation. So basically if we do the cross correlation of wavelet 1 with wavelet 2, so wavelet 1 is 2 comma 1 comma minus 1 comma 0 comma 0, and wavelet 2 is 0 comma 0 comma 2 comma 1 comma minus 1. So one thing to notice here is that in convolution we basically reverse uh, the wavelet and then do the progressive sliding past over the other waveform, whereas in correlation we don't do that. We just slide past the function as it is over the other. So we normally start sliding. So this is these are 4 5 plus 5 10 minus 1, so there will be 9 outputs, and the first is defined as the lag value of -4, and when they are directly over each other, like this zero lag, this is called a zero lag position. So this is how we cross correlate. So we starts with -4 lag position. So we do the cross multiplication. So -1 times 2 will give you -2, and then we do a time shift, go to the lag value of -3, and now we have to multiply 2 times 1 plus. So we do the summation of the cross multiplication products. So 2 times 1 is +2, and 1 times -1 is -1. 2 minus 1 will give you 1. So that's how we do the cross correlation. So we do the same for all of these, and you can see the cross correlation value for each of these lags. So here we can see that at 0 lag you have the value of -2, and at -2 lag we have the highest value, 6. So basically if we do a time shift of 2 samples, wavelet 2 by 2 samples, will get the maximum cross correlation. Now let's cross correlate wavelet 2 with wavelet 1. So this is cross correlation of wavelet 2 with wavelet 1. Again, you have the lag positions on the right, and the final summation of the cross multiplication products on the as the output. So again, we see that shift of two samples on the positive side will give you the highest value. One thing to notice here is that let's put these together. So this is the lag value, starts from -4 to 4, and when the wavelets are directly on top of each other is called the zero lag position. So on the left is wavelet 1 with wavelet 2, and on the right is wavelet 2 with wavelet 1. So we can see that they are not the same. So that means cross correlation is not commutative, like convolution is commutative. It doesn't matter if you convolve a wavelet 1 with wavelet 2 or wavelet 2 with wavelet 1. But with cross correlation, it's not commutative. That means they are not similar. So it's important to know what you are trying to do. Okay, so this is another example of so this is the function and you are trying to correlate with the waveform, and the question asked is to find out the likely position of the signal in the waveform. So again, we start doing the same process. We start slide past the signal function over the waveform, and then do the cross multiplications, and then do the summation. So you will get these values on the right. So we can see that we get a very high positive value of 11 uh, when we have the function, the signal function at this lag, at this time shift. So this is the position of likely position of the signal in the waveform. Okay. Now, if we cross correlate two identical non-periodic waveforms, your cross multiplication products will sum to give a maximum value at the zero lag position. So when you cross correlate two similar waveforms, you are likely to get the maximum value at the zero lag position, as you can see here. And if you have a time shift in your function, the value of these cross multiplication products will cancel out each other to give you small values. So basically the cross correlation function therefore peaks at zero lag and reduces to small values at large time shifts. So if you have time shifts, the value decreases. Okay. Another application of cross correlation is another point to make here is that like I said, if the two waveforms are similar, closely similar to each other, they produce a cross correlation function that is strongly peaked at zero lag. So it will peak at zero lag. And if you have two completely dissimilar waveforms, the cross correlated, the sum of the cross multiplication products will cancel out each other and gives you a zero value. So for example, if you cross correlate two traces with only the random noise, you are likely to get zero cross correlation. So basically, cross correlation function measures the degree of similarity of waveforms. Okay, another application of cross correlation is to detect detection of weak signals embedded in the noise. So for example, here you see a waveform have got signals concealed in the noise. So when you cross correlate a known signal function to this waveform, you will be able to detect the position of the signals in this waveform, like you can see here, S1, S2, and S3. So cross correlation is used to detect occurrences of a known signal concealed in the noise. Okay, so basically in seismic data processing, there are several instances where we do the cross correlation. So for example, after migration, the CMP gathers still have got some some misalignment of the traces on the far offsets or on the mid offsets. So basically, this process is known as trim statics, and we try to cross correlate a pilot trace with these near, mid, and far offset traces and try to compute the residual static shifts. And this helps in flattening the gathers. Another application of cross correlation is during the residual move out analysis, RMO, and trim statics. We used to QC the near and the far stacks, so to see how well correlated are they. So this is another example. Another example of cross correlation application is in the QC of the 4D surveys. So during the processing, we try to check for the repeatability of the base and the monitor surveys. I have an example on the next slide. So this is an example of the cross correlation of an horizon of a base and a monitor survey. So this is the normalized. So the largest value is divided to each of these values to in order to normalize. So it's between 0 and 1. So the purple color here shows strong correlation, and the green color here shows weak correlation. So looking at this QC, it looks like we have a decent uh, correlation. Basically, in 4D processing, we try to minimize the effects of acquisition and processing imprints on your data on the base and the monitor, and we try to maximize uh, the reservoir actual reservoir signal. So yeah, so this is how we use cross correlation in seismic data processing. There is a link for this if you want to go in more detail of this image. Okay, autocorrelation. Now if we this is a special case of cross correlation. So if we do the correlation of the data with itself or the seismic trace with itself, the output function is called autocorrelation function, and now is denoted by phi xx instead of phi xy. And this function is symmetric about the zero lag position. I have an example on the next slide to explain this thing. How is it symmetric? So basically, the autocorrelation function of a periodic waveform is also periodic with a frequency equal to the repetition frequency of the waveform. And the autocorrelation function is also useful in the detection of hidden periodicities in any given waveforms. I will cover these things in more detail in the next few slides. So basically, I said autocorrelation is correlation of the function with itself. So we slide past the same wavelet with itself. So for the wavelet 1 we have seen before, 2 comma 1 comma minus 1 comma 0 comma 0. So it's convolved, is correlated with itself. So here you can see that for these lag values, it peaks at the 0 lag value. 6 gives you a very high positive value, and then for minus 1 and 1 it gives you plus 1, and for minus 2 and plus 2 lag positions it gives you minus 2 and minus 2, and likewise. So it's basically symmetric about 0 lag position. It gives you the same values on either side. So this is an example of real air gun source signature in marine data. So when you do so here you can see the primary signal, and you see the ghost, the source ghost, and there is bubble energy here. So when you do the autocorrelation of this wavelet, the output function looks like that. So basically so it peaks at 0 lag value, but because of the limitation of the software not able to display the negative times, it shifts further down. But assuming that 0.4 is the 0 lag position, so here we see that it peaks at the 0 lag value, and then there are other peaks. You see the smaller peaks in the data, which are basically uh, the position of the bubble energy, so the peaks corresponding here, or uh, we will see in the next slide about the multiples. But here you have the bubble energy, which is roughly around from here you can see that between zero point 0.4 and zero point 0.3 is 100 milliseconds. So basically from 0 to, so the bubble energy is appearing around 100 milliseconds, like 0 0.1, which you are able to detect here. These kind of things are useful for designing the deconvolution parameters when we do the designature filter. So yeah, we need to preserve the signal sitting at zero lag position, and then we can design the deconvolution parameters based on the autocorrelation function. Okay, so basically this, like I said, the side lobes in the autocorrelation function are an indication of the existence of periodicities, like we have seen in the previous example. And these side lobes, the spacing of these side lobes defines the repetition period. So like I said in the previous example, this 100 millisecond is the repetition of this the bubble energy in your signal, in your wavelet. So the side lobes gives you the indication, that gives you the indication of the existing periodicities in your data. So here like it peaks at zero lag, and then you have got other smaller peaks. So these are basically either multiples or bubble energy or any other features in your data which is repeating in your data. So this is an example. This is a common channel display, and when you autocorrelate, this one gives you the autocorrelation function shown here. So basically we don't represent the negative side of the autocorrelation function, but just to show it's symmetric, it's displayed both sides. So here you can see that the primary signal, and then there is some geology underneath. So this is the seabed, and this is some geology underneath. So you can see that seabed is around 0.5 milliseconds. So you expect your first bounce around 1 millisecond. So like this event is likely to be the multiple energy, and these are the multiples of the underlying geology on this display here. So when you do the autocorrelation, so when at the zero lag you get this peak, and then around so this is 500 milliseconds. So around 500 milliseconds you see the first bounce, this multiple energy here, and this followed by the multiple of the geology underneath. So this autocorrelation function can help you uh, detect the periodicities in your data. Also, sometimes we use the autocorrelation function to pick the first bounce, which is also the period of, which is also the timing of your seabed. So because sometimes in shallow water data we are not able to record the water bottom accurately. So what we do is we autocorrelate the data and detect the position of the first bounce and pick the timing of this first bounce, and this first bounce multiple gives you the timing of the water bottom in your data. So this is used to pick the water bottom also. So this is one of the use of autocorrelation. This is another example. Like this is a stack. This is a stack of data of 2D line maybe, and then when you autocorrelate, it will help you finding the position of the first, second, third bounces of the multiples. So this is the link for this image. If you want to have more details of this image, you can go through this link. Okay, this is another very good example of application of autocorrelation. So basically we use it to QC the deghosted and the designature data. So here you can see, so this is the the autocorrelation of deghosted data. So here you can see the small this fading low frequency energy appearing every constant interval. So, and this is on the right. This is after designature, after removing the bubble energy. Basically, this is the bubble energy. After deghosting, you can see the bubble energy very clearly. And when you do the designature, you can see that this bubble energy is removed. So that means this is an effective designature process. So we normally do autocorrelation during this designature and deghosting and designature process. Okay, if you want to go into more details, you can go through this link. Another important application of autocorrelation is basically when you autocorrelate, you are basically multiplying the amplitudes. So is squaring the amplitudes, which is also uh, a power terms. So square of the amplitudes in frequency domain gives you the power or the energy contained in the frequency component. So basically autocorrelation function can also be used to compute the power spectrum of a waveform. So there are certain applications of autocorrelation. Like I said, I've shown you it's used for QCing the deghosting and designature processes. I've explained you it's also used for picking water bottom horizon in shallow water data sets because it's not very well recorded in the shallow water data, the water bottom. And autocorrelation helps in determining the tau p deconvolution parameters for shallow water demultiple. So basically for deconvolution, you use the autocorrelation to design the gap and the operator length parameters in deconvolution. Okay, so here is the summary of what we just talked about today. So correlation is basically another time domain operation and is equivalent to multiplication of amplitudes and subtraction of phase spectra. Whereas in convolution, you basically convolution is equivalent to multiplication of amplitudes and addition of phase spectra. In cross correlation, it involves subtraction of phase spectra. That's why when we do the autocorrelation, of a trace with itself, the phase is always zero. So basically autocorrelation function is a zero phase function. Another point is cross correlation is not commutative, so it's important if you're correlating wavelet 1 with wavelet 2 or wavelet 2 with wavelet 1. So depending, you will get different results. Is basically a function of the measure of the degree of similarity of waveforms we have seen. It helps in the detection of the weak signals embedded in noise. Autocorrelation function is symmetric about the zero lag position and is zero phase, and is also used for the detection of hidden periodicities in the data. And the autocorrelation function is used to compute the power spectrum of a waveform. Like we have seen that it's basically the square of the amplitudes, and which is basically the power term. Okay, so the references for this presentation is the books by Philip Keary, Michael Brooks, and Jan Hill, An Introduction to Exploration Geophysics, and Seismic Data Analysis by Ilmaz. So if you want to go in more details, you can review uh, these books to find more details. Okay, thank you very much. Good luck.